Thank you, everyone, for joining. Sean, thank you. We really appreciate you joining us today for the Advancements in Geothermal Technology webinar hosted by the U.S. Department of Energy Geothermal Technology Office, as well as research Bill Peter from Oak Ridge National Laboratory and Jin Su from Sandia National Laboratory. Sean, do you want to go ahead and kick us off? I think we can go ahead and get started.
Great. Well, welcome everybody. Really happy to have everybody here join us virtually. My name is Sean Porce. I am the Data Modeling Analysis Lead for the U.S. Department of Energy Geothermal Technologies Office. I'm also the American-Made Geothermal Manufacturing Prize Lead. And that is the program that is supporting today's webinar, as well as the agenda, where we hope to focus on an exciting discussion on how additive manufacturing innovations can improve geothermal tool design and fabrication. To dive into this topic, we have two exciting presentations from folks from our national laboratories, specifically Oak Ridge National Lab, as well as Sandia. So just a little bit about our agenda here briefly. We're going to kick off our webinar. I'll give a little bit of an overview about the Geothermal Manufacturing Prize, what it's all about, and how you can actually still join the set competition, which is live right now. Then we'll be welcoming Dr. Bill Peter, who's the director of the Manufacturing Demonstration Facility in Oak Ridge, to discuss research innovations that use additive for the benefit of geothermal technologies, more particularly focusing on heat exchanger design, as well as how to prevent surface wear downhole. And then from there, we're going to hand things over to Dr. Jin Su, who's a principal member of the technical staff at Sandia National Laboratories, and he'll be presenting on his team's collaboration with Oak Ridge to incorporate additive in the design and development of a percussive hammer drill. And after that, we'll have a bit of a Q&A and hopefully have a great discussion. So just a little bit about housekeeping. You heard it a couple minutes ago, but please make sure your mics are muted, as well as keep your cameras off in order to maintain bandwidth for the platform. If you do have a question, you can select all panelists on the right-hand side under the Q&A tab in your WebEx application. You can type your question in there, and one of the folks here participating as a panelist today will capture your question, and we'll make it available to folks during the chat here after the presentation. Just as a reminder, the webinar is being recorded, and it's going to be made available afterwards on the HeroX Prize website. So now, without further ado, I'd like to just go into a little bit about the Geothermal Manufacturing Prize, as well as the set contest that's currently live. So for those who may not be familiar, the Geothermal Manufacturing Prize is a set of 4 contests seeking to leverage additive manufacturing innovations in order to push the bounds on how we can build and design geothermal tools. Along the way, we're offering $4.65 million in incentives in the form of cash, vouchers, as well as field testing costs in order to incentivize competitors to come up with new designs and ideas. Not only that, but the program is supported by a national network of support organizations through the American-Made Network. This is an ever-growing list of over 130 energy incubators, investors, universities, national laboratories, including those participating today, as well as others who can help, who have the wherewithal and resources to help participants achieve their goals. So we're going about cultivating these ideas through a series of 4 escalating contests. Ready, Set, Make, and Geo. We have already completed Ready, which was launched in April of 2020, and we announced winners at the Geothermal Rising Virtual Conference back in mid-October of 2020. These 4 escalating challenges are walking the path in manufacturing innovations, where we ask competitors to come up with a design, a concept, a design, ultimately create a prototype, and then test an advanced prototype at geothermal type conditions. Currently, we are in the midst of SET, which launched last October, and applications for SET are due on February 17th of this year, so we have just about a month to go before the application deadline, and we'll plan to announce winners in April 2021. After which, Make and Geo will continue for the remainder of 2021, and we'll be announcing grand prize winners sometime in the summer of 2022. If you'd like to learn more, the HeroX.com website there at the bottom is a great resource to understand everything there is about the prize, including rules and guidelines on how to enter. So a little bit about the contest incentives that we're offering. As I mentioned, we have completed the Ready contest, where 15 teams split a prize pool of $500,000. In stage 2 of the contest, known as sets, we are going to be awarding up to 10 winners between $100,000 and $200,000 in cash, as well as a $75,000 voucher that could be used to redeem towards technical assistance at national laboratories, as well as other organizations that are participating in the American Navy. I want to note that what's really great about this is what's really great about the timing for this webinar today is that SET is an open competition. In other words, you do not need to have one ready, nor did you need to have submitted an application previously in order to participate. So anyone can still join and submit an application by that February 17th deadline, and encourage you to check out more information on the website, and happy to have you on the call here today in order to learn more about our prize competition. And without further ado, though, I want to hand it over to our technical experts here on the call today. Really happy to have Bill as well as Jim talk a lot about their great sets of innovation they'd love to discuss. So with that, Bill, I'd ask you to probably help start sharing your screen and turning it over, and look forward to your conversation.
Sure. Let me see. There we go. Give me 1 second. Are you able to see my screen now?
I am, yeah.
Okay, very good. So, welcome. Thank you very much for giving me an opportunity to speak. My name is Bill Peter. I'm the director for the Manufacturing Demonstration Facility. I'm going to talk today about 2 different projects that we had. One that was much more about design and how it impacted geothermal, and another that was more on the materials aspects, each using additive manufacturing to come up with solutions that were unique compared to conventional technologies or ways that we would think about it. And hopefully that'll give some different case studies as to how you can utilize these technologies. So the MDF is, it's called the Manufacturing Demonstration Facility. Our core research funding is by the Advanced Manufacturing Office to do fundamental research in advanced manufacturing, including areas like additive. We have over 100 pieces of equipment and over 100 staff members that are working on these technologies every day, which gives us a great insight in being able to go through and look across the technologies as to where some of the big problems that national laboratories such as Oak Ridge can help solve issues as we move forward into it. But this also allows us to collaborate with the other national laboratories on some of these big problem sets. We're doing work in composites, ceramics, metal systems, and I'll talk through that. The 100 pieces of equipment, most of it is actually put at no cost to the laboratory, over 60%, at the facility for us to work hand in hand with industry. We have over 200 collaborations with industry that we've been working on the technologies themselves to try to help further develop them, create new supply chains. And so with that, learning from the collaborators we have, our industry partners, we're able to go through and really make sure that we are helping solve those major issues where there's need for acceleration or we need to help in development of the supply chain. There are other mechanisms to work with us called industry collaborations. We start about 30 new projects per year with companies. That's outside of the geothermal prize that we're talking today, but another opportunity for companies to work with us. Whoop, sorry. As far as the types of technologies, and I'm going to talk briefly about these only to give you some sense. Of course, we're doing work in things like powder bed additive manufacturing and fused deposition modeling with polymers. These are areas that quite a few of you are probably very familiar with, but we're also pushing the boundary of what can we do with these systems and creating really large polymer and composite printers, looking at how we can get larger in scale as we get into things like large metal printers, how machining and additive in connection can make better parts. And then also looking at other technologies like the one that's down in the center of our slide is SkyBAM. This is a concrete printer where we can make really large parts in deposit tonnage per hour of concrete material down as we're going through and building up large sections. With all of this, we are developing a digital factory where we are capturing information as we deposit to make sure that we learn about these systems, learn about the materials, and how to enhance the performance of the finished or final components, subsystems, or infrastructure that we build using these technologies. We played an important role, even though we're funded by Advanced Manufacturing Office, we spend a lot of time working with other offices such as Geothermal to try to see how we impact some of the impact different industries. And on the right, I'm going to spend most of my time talking about geothermal, but on the right shows several of the different areas that we've had impacts across the board, from helping to build molds that go into boat hull fabrication, to precast concrete industry, to direct deposition of turbine components that are going into land-based engines, even to looking at nuclear and how we have impacts in nuclear. So very quick shot at everything from direct fabrication, rapid prototyping, to tools, dies, and molds. What and how would I want to look at for additive as we start thinking about it in energy systems and specifically in geothermal? Well, there's a number of areas we've seen improvements as you use additive, and this is in the multi-year program plan for the Advanced Manufacturing Office at DOE, where it really talks about how do we think about new innovations, part consolidation, lower energy consumption, less waste, reduced time to market, lightweighting, agility. These are all reasons to start going through and developing this. I'm going to spend a lot more time in improving performance in the innovation segment of this, as well as look at the idea of what we can do from a performance on the heat exchange within additive. But there's other factors as we go through and look at the design using additive. One of the things that you really want to do is get away from the conventional way you would design the parts and start thinking about how these processes may be able to be utilized to really further enhance it, not build the same part you were using other technologies. And we spend a lot of time doing that, and love to talk to you further about ways that you can improve on that. One of the things, and I talked a little bit about this as we got in the technology slide showing the different systems that we're developing, is that we can look at metals, polymers, and even ceramics, which aren't on here, and start thinking about smaller systems that resolution is really the key aspect of what we're trying to do. So you may be thinking small components, but high fidelity, or going into large additive systems where we really increase the deposition rate. You still can go through and get capture resolution or other activities as you do this, but usually there's quite a difference as we get into larger systems. There's more of a demand or push towards at what rates can we deposit and how it competes with conventional methodologies, especially as you start getting into really large systems or components. So I'm going to start into one of my case studies, and that's around the design of heat exchangers for geothermal. The goal of this project was really trying to see, could you, for about the same cost, increase the baseline of heat transfer coefficient by 2x? How far can we go with taking new designs in a similar volume at a similar cost and really be able to take advantage of the new aspects of the geometry that you can enable through this? And of course, this has huge impacts as we start thinking about the equivalent cost as we start thinking about energy, electricity or energy production from geothermal systems. And so really trying to go through and push how far can we go within the efficiencies of those systems, thinking of these novel designs. One of the key aspects as we go through this project is that we really wanted to utilize everything from design and using computational tools to rapidly being able to build the parts and test them inside of a platform that we can compare to traditional heat exchanger designs. And so that's what this project was about. Some of the things that we found as we did this was that triangular and counterflow systems are really important for going through and looking at the efficiencies of where we can get within these. And so this is an example of one of the geometries that was developed. It's actually very close to the winning geometry I'll show you in just 1 second that improved performance. But part of this is the lessons learned as we go through this. So you have the simulation tools to help inform. You're building it rapidly, evaluating how easy is it to fabricate these things, and then testing it and giving feedback into the models that we're developing, which really helps us get to the end. The other thing is trying to look at how narrow the diameter of this had impact as well as we were going through and trying to design these heat exchangers. We went through inside that test cell, we went through and did testing, and we basically found that for this heat exchanger design that you're seeing right here, we ended up overall having heat transfer coefficient that was about 32% higher than what we were seeing for traditional. Do I believe this is the final optimized scenario? No, I think we could continue to go down this pathway, but gives an example of how you can start to go through and show tremendous impacts within the similar volume. By the way, that test cell I was showing you about allows us to try different flow rates and different geometries. I'm not just stuck on looking at this type of geometry for a heat exchanger. We've worked on actually in parallel a lot of other projects that we're looking at both heat exchange and fluid flow. These are some examples that may be of interest, everything from impellers, where we showed weight savings and reduction in machining and hydraulic efficiencies, to power electronics and how you could cool in a smaller, about a third the volume, to even more recently, we've started developing new microreactors where we're really trying to change the way we look at heat exchange within a reactor and look at the cost and reliability by using in situ data analytics as we build the part. While I was talking about design, the other aspect here is looking at what new novel material and material combinations should we start thinking about as we use these technologies. Inside the MDF, we've started developing new steels. We've been looking at new aluminum alloys that go up to much higher temperatures, looking at like 400 C with lightweight materials. Ceramics, refractory metals, and nickel superalloys. A lot of these materials that historically have been very difficult to fabricate and form, we can start using additive techniques to get into these net shapes that are needed, as well as polymeric structures and composite type structures through these means. One example of this, and this was a funded geothermal project that we worked on a number of years ago. This was an earlier project, but this was with looking at amorphous alloy materials, iron-based, that we could go through and we could fabricate in bulk these powders. In this case, we had done a lot of work with Carpenter to go through and produce the powders. Then either take those powders and consolidate them into monolithic parts, or you could use laser directed energy deposition to deposit those down and start making additive parts, or even look at cladded parts using these type of technologies. The benefit is by going through and creating this very fine microstructure, we could greatly increase the hardness values, as well as looking at improving wear resistance and corrosion. So these were compositions that we knew as they devitrified and crystallized would become stainless steels, and wanted to look at them for these type of applications. While the monolithic material systems are very interesting, actually where I believe the biggest impacts are really looking at where we can go through and look at graded structures, deposit these within steels, and show very wear-resistant surfaces associated with these. These are some of the results that we went through on this project, where we showed that compared to stainless steel and compared to stainless steels, that when we started doing cyclic polarization tests, one of the really amazing things, because of the fine microstructure, you actually don't get pitting. So we're not getting localized pitting corrosion that occurs in a lot of the stainless steels you use. We also did salt fog tests to go through and compare this to some of the tool steels that you may look at, like 4340 and H13. On top of that, we really wanted to look at the fracture toughness and hardness. And in these cases, we compared it to a higher cobalt percentage, like 20% cobalt for tungsten carbide cobalt, and found that we could get hardness values that were in league with the tungsten carbide cobalt, along with fracture toughness that were close to there. They're slightly more brittle than you would expect with the tungsten carbide cobalt, but some really interesting materials. The overall interest, though, was then taking those materials and seeing could I bond those and get a metallurgical bond, so very intact, and fuse these materials down onto steel substrates. And this is an example where we use laser deposition to go through and be able to fuse these coatings down. We showed that our hardness values as we did this increased the base material. And these are hard steels as we begin with. On a Vickers, about 200. We can get about 4x increase in the material properties as we use this. We then went through and started doing some abrasive wear tests. This is just an example of this, where you start showing drastic increases, about a 5 times decrease in what we were seeing for abrasive wear, as you can see, comparing the laser fuse coating on H13 versus what you would see for H13 by itself. Obviously, in this scenario, the smaller the bar is, the better you're at. You can also start to see the comparisons with the tungsten carbide cobalt as we were looking at fully dense material. Hence why I really think the sweet spot is how you use these as materials to surface some of the steels we're looking at. I want to go through and just follow up by stating that one of the big areas as we do this is starting to look at hybrid structures and graded scenarios. So I gave you one example. Really the future to me in additive for where we can use and enhance performance is how you use these multi-material scenarios. And for gears, we've shown scenarios where we made titanium alloy central portions of the gear, but then used TI64 B4C material, so a composite material on the outside, drastically increasing the hardness and wear resistance of that gear. We've shown in tungsten carbide cobalt where we can modify or look at infiltrants and infiltrate with either a nickel or steel, and you can start thinking about graded structures as we do this. In large-scale metal deposition, we've gone through and shown how we can take a mild steel and then be able to fuse down a stainless steel on the outside as we start building these materials. And we've also shown transition joints between austenitic and ferritic materials, typically very difficult to join materials, that through grading the compositions, you can actually get to a solution where you join those together. I have different examples as you go through this and looking at multi-material, what type of geometries, but I'm going to stop at that point. I wanted to at least introduce these type of subjects to you and show that there are opportunities through additive to be able to go through and think about multi-material solutions, not just in the same class of materials, but even thinking about things like ceramics and metals, ceramics and polymers, or metals and ceramics. Thank you very much. If at all you'd like to get in touch with me, please do. You can get my contact information. We also offer virtual tours of our facility at the address that you see right there. If you guys have interest in a certain technology, you can go on a virtual tour and be able to see the equipment and listen to videos from our personnel or staff on some of the projects they're working on. Thank you very much.
Thanks, Bill. And yeah, having taken a virtual tour and having taken a real life tour, it's of course not the same as seeing the MDF in real life, but it's pretty darn close. It's a great resource. So I encourage folks to check it out. With that, again, we're gonna hold questions for Bill until after Jim's talk. So would, Jack, if you don't mind, go ahead and keep going, and I'm allowing Jin to go ahead and start sharing his screen. And while Jin's getting prepared here, I want to note that one of the real highlights of the collaboration between these two organizations is really hopefully going to be serving as inspiration for those of you who are either actively working in and participating in the SET competition, or for those of you who are looking to think about how additive could play a role in your respective technology spaces. The work that Sandia and Oak Ridge kind of put forward in a collaboration space to make what Jim's about to talk about a reality is really the hopefully a really good, interesting sort of case study to think about when you're considering your topic. So look forward to hearing Jim talk a little bit more, and please go ahead and take it away, Jim.
Can everybody see my screen?
Mm-hmm.
All right, thanks for that intro, Sean. Yeah, I reiterate what Sean is saying. If you haven't had a chance to see the MDF in person or take a tour, it's really worth the visit. There's a lot to see there. All right, thanks, Sean. So today I'll talk about one of the case studies that we've gone through working with Oak Ridge. I think Bill mentioned talked a lot about the overall capabilities of additive, where the advances can be made, and I'll talk about specifically one of the areas of one of the case studies that we looked at in terms of how do we take advantage of additive in a geothermal environment. So let's see, I'll go over a little bit of background about what we're going to be talking about, talk about some of the design details that we're addressing, show some of the fabrication and testing that's going on currently, and then what's going to happen afterwards. So a little bit of background. So Sandia has been working in drilling for quite a long time now, probably the last decade and a half or so. We've had a little bit of a focus in accessing harsh environments or subsurface harsh environments, especially with respect to the hard rock. And a lot of the focus there has been directed at percussive hammer drilling. A lot of the applications that we were interested in, probably since the mid-2000s, have focused on areas where the hard rock environment is the target, and we need to get there really quickly. So some of the work that we've done since then is really focused on how quickly can we get through the rock. And at the time, Jerome Polsky, who's currently at Oak Ridge, was focused on drilling through the rock as quickly as possible. And at the time, again, I mentioned, it really was the interest was, okay, what sort of rock reduction methods give us the fastest penetration rates? But eventually the research turned into a application where, okay, how do we deploy this in a real system? And then we had to address, okay, so, typical drilling operation, if you're deploying a system, you're going to need some downhole rotation or rotation. And the conventional methods of generating rotation are either from the surface using a top drive or a Kelly, or if you're doing some directional drilling, a more common approach might be having a positive displacement motor or a PDM downhole in conjunction with your drill bit. So for the application that we were interested in, we were looking at a continuous feed system, so that sort of eliminated our ability to rotate from the top, and that forced us into the situation where we needed downhole rotation. So for the environments that we're looking at high temperature. So the PDMs, if they're conventional elastomer rotor and stator sections, were a little bit out of the question. So we had to look internally to see, okay, what can we actually do to generate rotation downhole to allow us to deploy the system in the fashion that we needed to. So ultimately, what we needed was to combine our fast drilling that was enabled by percussive hammers with some sort of downhole rotation system. So internally, we explored several options. One of the concepts that we ended up pursuing was what would eventually be what we called internally our auto indexer. What it is essentially elastomer-free motor It provides high peak torque in a small form factor, which was ideal for coupling with a percussive hammer. We were trying to get performance targets comparable to a positive displacement motor. So we're looking at, about 1,000 foot-pounds or so, somewhere 1,000 and 2,000 foot-pounds of torque, at least for the size of tool that we're drilling. And then we also needed to work in high temperature. Ultimately, that's what our environment was. So at the time, our temperature, it was actually funded through another customer, but the work that we ended up doing had a lot of overlap with the work that we were doing in geothermal as well. So just a quick illustration of what this tool is actually doing. So this illustration is going to show the internal components of the indexer tool working and how it would advance the drill bit. So you see the main portion of the tool is actually driven by a vane motor. And for those of you who are familiar with vane motors, they're basically a rotor housed in an offset housing, which creates a differential pressure as the rotor's spinning, and the differential pressure creates the torque. So the torque is transmitted from the motor through what we call these dogs, or the drive system, and then if you look on the right side of the animation, you'll see an incremental advancement in the drill bit. So when I talk about this particular motor, it's a little bit different than what you'd see in a conventional motor, in the sense that the output, or the rotational output that you see, is incremental as opposed to a continuous rotation. Now, when using this in, say, like a conventional drilling application with like a PDC or roller cone, this may not be that well suited to that application. But for percussive hammers, where you have a cycling of the piston striking the bit to generate cuttings, it actually is it's well suited to that particular application. So I have another video here that shows the actual tool in motion. So you can, oops, sorry, let's see. Okay, so you'll see the tool spinning here to get a sense of what I'm talking about when I talk about the incremental rotation. I'll play it one more time. So you can see the tool itself is it's kind of violent when it operates, and that's one of the design challenges, is finding materials and designing it in a way that it'll actually survive when it's operating. So based on some of the design requirements, largely being the characteristics we're looking for are hardness. There's a lot of surface contact between the various components, and we're operating this dry, so we need good surface finishes, and also toughness. You see that there's a lot of repeated loading, so you have fatigue is also a consideration. So, based on these original considerations and what we knew at the time when we originally developed this thing, is that, in order to survive the environment we're looking at, we're probably going to need some sort of steel. And what we ended up using in our original design was carburized steel. So this piece that you're seeing here in this picture is the rotor. It's about 3 inches in diameter and about almost about 5 inches long when you consider the shafts on either end. So this particular part, based on the way it was constructed, resulted in a moment of inertia of about 0.025 kilogram meter squared. So what that means is that it takes a certain amount of torque to accelerate this tool to generate the output that we need. So, again, based on the design constraints and the manufacturing constraints at the time, this is the resulting tool that we had. So probably about a year and a half ago, I think we started looking into ways that we could potentially use additive to make improvements in tool design. And so Sean asked us to, take a look at what we could do working with Oak Ridge. So one of the things we thought about was, in this particular case, we could make some improvements in our tool if we could sort of reduce the the rotating mass a little bit. And until we thought about potentially doing this with additive, it really wasn't possible because of the constraints of the requirements for hardness and toughness and overall material properties. So one of the things we did when we looked at this with Oak Ridge was like, hey, what can we do to make this better? And one of the things they brought up was, okay, we can do some topology optimization, right? If we're trying to make this thing spin faster with the same input, we can reduce the overall rotating mass. And that's one of the things that they took a look at for us. So based on some of these design improvements, knowing that you could build this thing in a different way, we were able to reduce the rotational inertia by quite a bit. So it's almost 60% less using a topology optimized design compared to conventional build. So we still needed the same material properties that we had based on our initial selection. So one of the things that we looked at in terms of material type was this the Meraging steel. We actually ended up going with the 300 series Meraging steel. That's built using powder deposition. So I think one thing Bill touched on earlier when he was talking about, we don't necessarily just want to build parts out of additive because we can build parts using additive. That doesn't really provide us much benefit. I think, looking at what we did and sort of how you can maybe get the most benefits out of some of this stuff is that you must have to look at it from a whole entire redesign perspective, right? Like, so in our particular case, we looked at one piece part of the system, and we see that we have some performance benefits based on our models, but they're not as the performance benefits aren't as high as you could get if you had optimized around the whole system as opposed to just optimizing around one piece part. But I think in this particular case, it was still beneficial in the sense that we do see performance improvement in our initial models, and that we're going to try to test this out and see how things go. So for those of you who haven't seen powder deposition operation, this is a short video of the part as it was being built layer by layer. Come on. Cannot play media. Oh, man. All right, so that's a dud. Sorry about that. What you'd see here is the laser rasterizing around the various layers. It's securing the part, and then there's I guess a sweeper that comes across, puts on a new layer of material, and then it builds up layer by layer. So I apologize for this video not working. But in the end, here's the end result of what we've built, or what Oak Ridge has built for us. On the left is the part. So for the vane motor build, it does require some pretty tight tolerances. So we do have to have some post-process machining. So the part on the left is as built from the 3D, the polymer deposition, and powder bed fusion build process. And on the right is our post-machined part. So for those of you who have a sharp eye on manufacturing, you might notice there might be a little bit of a defect there. We did have a little bit of an incident when we were doing some of our post-process machining. We had an accident on the outer surface finish on the final OD. So fortunately in this case, this is along the axis, so it's not going to cause us too much problem. But it was an unfortunate incident when we were doing some post-process machining. But for the particular build that we were looking at, we did have to still have the post-process machining, but we did have the better rotational inertial properties for our part. So what's next? There's some tests that we want to run to compare the standard part versus the additive manufacturing topology optimized part. Some of this will be control testing on our Sandia dynamometer. We're going to run some tests of the vane motor by itself to see how it performs under load, either with the with both the topology optimized part and then the standard part. And then if things show promise, we'd like to take it to our Sandia high operating temperature drilling facility and run some tests there to see how well it actually performs in a drilling environment. So with that, I think that's all I've got for our case study. Sean, if you have any questions or anybody else has any questions, feel free to ask.
Thank you, Jen. Jackie, if you don't mind, oh, there we go. I am sharing my screen again. And never fear, Jen, I actually was able to find hopefully a working video. Hopefully folks can see this. Illustrative of really obviously just the cool technology at work here, but also honestly the manifestation of what is a year-and-a-half collaboration that sort of went into sort of building this. So a lot of great work and a lot of great focus from Jim and from Bill and his colleagues and Jerome and everyone else at Oak Ridge and between Sandia. So we look forward to sort of seeing the finished piece and hope testing goes well.
Sean, I'll add that this technology is add-up system that was originally designed for use or looking at tooling in automotive applications. One of the items as we go through and look at that technology is that it allows us for relatively high resolution parts. In fact, the thinnest structure we've been able to make with it is about 100 or 200 micrometers. And so really trying to go through and look at high resolution, advanced steel fabrication. We've done a lot of work inside that system.
That's excellent. All right, so we have entered sort of the Q&A portion, so I encourage folks who wish to ask some questions of our participants here today to go ahead and populate our Q&A box there. I think we have a few in here already. I know folks have been actually, it looks like, answering some questions as we've been sort of receiving them. As far as prize administrative ones go, it looks like Emily and Jackie, thank you. You have been able to answer those questions as we've kind of gone through. And Bill, I know you had a chance to sort of respond to folks' discussions around multi-material sort of and grading sort of pieces. I'm curious if you can go into a little bit more on the challenges associated with bonding between ceramics and metals or gradation properties and the additive sort of focus in that world and sort of where we are right now or where do you think we can kind of get to?
Yeah, so the previous technology that we were doing were gas atomizing, and we had just started getting into directed energy deposition where you could modify or grade the material as you went along. A lot of that earlier work was that project ended, just to give some idea, in about 2012, 2013. The activities associated with that were really looking more of a cladding type process. Additive allows us to modify or change the chemistry as we go along. And a lot of the new printers that are in directed energy deposition allow you to take more than one powder feedstock at a time. So you can layer by layer blend or modify that. One of the issues we'd run into is that as you built that part, I had to heat the substrate in order to go through and keep the material from cracking as you cool it from some of the changes in the coefficient of thermal expansion as you cool the component. As I look at graded structures, similar to what I showed in the slide after that, you can actually get into scenarios where you make slight chemistry modifications and finally get it up to a full chemistry of the amorphous material. I was asked about the cost structure with it. One of the things we're trying to do is make sure that we understand the overall cost of the entire process, so that you can break it down as we're trying to look at additive, what makes sense, what doesn't make sense. Are there ways I would change that geometry, as well as those feedstocks. That was a gas atomized powder. The fact that it is a steel or iron-based material actually meant that it really wasn't a high-cost powder, but there are things like argon and other things that are associated with gas atomization that can make that a little bit more expensive. Frankly, for a given geometry and scenario, you'd want to take a look at it, see what the overall cost strategy is, both for production of that part, but the other part that people sometimes fail to look at is life cycle costs. So what is the cost associated with failure, replacing that, and if I can get a certain X percentage increase in lifetime of that part, will you be able to meet that bogey and actually improve overall profits by being able to go through and keep part replacement down.
Mm-hmm.
So those are some of the aspects I think is advancing this to take a look at. It also would be good. Most of what we were doing was on coupon samples and testing things out. We did some work on tunnel boring disc cutters. We also did some on paddles for aggregate breakdown, but we really haven't done anything that actually went downhole for specific geothermal application. But anyways, willing to talk further about the technology and how we may be able to get connected with that. I do use that as an example. I think there's a lot of chemistries and material solutions that have come out since then with high entropy alloys and other things that you may want to take a look at as we go down that pathway to see what the right material system is.
Absolutely. Yeah, it's everything that I've worked in this space just barely for only a few years now, and it's amazing the progress that's been made, and having seen the progress and the quality of the work and applications and competitors we have in the prize, I think that is also emblematic of where we see this industry going, which is really exciting.
There was also a question about heat exchangers. I did provide in the sidebar in the Q&A 2 references to papers that came out on this heat exchanger, in case there's anybody that would like to take a look at those. And obviously, if somebody wants to connect with me directly, we can go through, and there's other papers and other information that I could share on heat exchangers, but at least gave 2 references for that specific project if anybody wants to read the lessons learned or some of the advancements that happened during that project.
So I'm noticing, Bill, we also have some questions in the chat as well. And one actually asking about sort of laser powder bed for gradational solutions, and wasn't aware of the challenges or opportunities associated with different materials and being available for each deposition suite. Is that capable right now, or is that sort of yet to be tapped?
There are certain companies trying to look at it. I think it's a little earlier. As far as commercial solutions, it's a little harder to come by at this point in time for the powder bed systems. There's intellectual property, including Oak Ridge has got certain intellectual property that they've developed in thinking about multi-material deposition. But it is, most of what I showed it with these multiple materials had to do with really looking at directed energy deposition. Some of these either extrusion-based systems or methodologies where you're putting down the material into a melt pool. I do, and I don't know if I can share my slides. I will show you, though, even in binder jets, I had a project I didn't share here. Can I? Oh, yeah, thank you. Share. So I don't know if you're able to see the slide, but this is an example. You can look at scenarios, and this isn't graded, but look at infiltrate type scenarios. So in this case, we use some of those stainless amorphous powders that devitrified. We centered them such that you had interconnection between those, and then infiltrated it with a bronze material. Trying to come up with a very quick methodology to getting wear-resistant parts. One that has been tried out and made as an example by one binder jet company, X1, that we have had a long collaboration with. They did a stator where they used stainless and a bronze matrix, and by doing that would get sand particulates or silica into the softer material. It would create a hard sacrificial layer that would actually improve the overall performance of this. In fact, if you go to the X1 site, you can see a case study on this. Compared to this, where we're looking at a stainless steel, we've shown that you can get about a 5 times increase in the hardness values of the material as we start thinking about using something like these nanocomposite materials. Just one example of a hybrid structure that you could utilize. It is a powder bed. It is not, though, looking at it specifically for graded structures, which obviously directed energy deposition, some of these others make perfect sense. But just wanted to share that as sort of an example.
Yeah.
I don't know how to stop sharing, sorry.
Another question for you, Bill, regarding sort of printing resolution. And can you talk a little bit about the capabilities right now in the industry for printing and depositing for sensors and circuitry and electronic components?
Yeah, so there's different techniques that people are utilizing. If I go into a lot of like the laser powder bed and what you're doing in those type of scenarios, I mentioned sort of the resolution limits, which are around 100, 200 micrometers. And a lot of this has to do with your powder distribution and the size of the incoming energy source. However, if you want to get into nanometers, there's been a lot of work in finer resolution laser systems and directed right type techniques. And in fact, we've had some work and had success with a company called Molex looking at really low temperature sensors for temperature, humidity. We've also done things like acoustic wave sensors where basically I want to lay down a grid type structure, be able to put energy in and then look at the diffraction off of a grid system. Where you want to get into very fine resolution. And as you get into some of these laser systems that are more on the direct right, you can get into the nanometer type scenario. You always end up paying for it, though. Quite often, I'm either looking at resolution versus deposition rates. And so obviously, if I'm looking at sensors, I may not need the deposition rates, but we do need to be thinking about high production values and how you get there.
Absolutely. Thank you, Bill. It looks like there's maybe a few more administrative focused questions in the chat. I do want to actually, my role as moderator here, I'd like to actually ask a question again, though, regarding your comment where you sort of said this is obviously the rotor example is but one part of your overall hammer percussive drill. So going back through that exercise, can you talk a little bit about your thoughts around how you would think about an additive approach for more components, including that drill, or just in general, sort of the entire assembly and setup?
Yeah, well, I think specifically, so that rotor is attached to another component, and that component currently is manufactured using the standard manufacturing techniques, and it's got a lot more mass than the rotor. So even though we had some good significant mass or rotating mass savings on the rotor, it's still attached to another component in the system that's essentially weighing it down. So from a system perspective, if we could print those two together, potentially integrate some of these components into a unified part, or even some of the other system components, I think the benefits of additive would be more obviously realized. So just building it one part at a time in a system that wasn't necessarily designed for it. Really, like Bill, going back to what Bill said, it really, you need to look at it from an overall system perspective, not just piece by piece.
Yep, definitely excellent importance. And Bill, we do have just a general question here about sort of examples of where the types of materials, stainless steels, and alloys that you discussed today are sort of being used in different application spaces. I don't know if there's an efficient website or summary document that probably has some of that information. I'm sure the list is long, and I'm sure it's comprehensive.
Yeah, it depends on the maturity level on some of these. We have different examples in working with like EPRI, where we've had reports or papers that have come out in looking at transition materials. One of the reasons in looking at transition for austenitic and ferritic is as you get out in the field, the complication in trying to join those materials, and can you evaluate those. That is something in which we're still midstream. We've been developing it, working with it. One of the areas to go to is if you go to the MDF site, that's ornl.gov/MDF, you will be able to see there's an industry link, you'll be able to actually see our old project reports. So every project report we have, we submit onto there. And there's actually quite a few that hit that point. In fact, the gear that I was showing with the Ty-6-4 with the wear-resistant edge, that's an area that we publish a report with the company on, that you can go through and read that report. So there's several things out there. We also show all of our publications on our website that are not reports, but going out and are published in literature. And so you can, by going to our website, see all of our papers and see if there's things that you want to download or take a look at to get a better sense of it.
Thank you. Looks like we have one final question here, just before nearing the end of our hour here. A question, Jen, for your sort of consideration. Do you have a fully optimized rotor and a selective materials design that you would have liked to have printed if you were not limited by currently known additive processes?
Potentially, I think one of the big advantages that we were looking at was the reduction in mass while still maintaining the strength properties. That could potentially even have been achieved, I say, like using, titanium or something like that. For that particular application, in my mind now, I can't really think of any additional benefits of another type of additive approach. Obviously these things are long and skinny. Overall, the assemblies are very long and skinny. So if we could build all these components in additive manufacturing method, or using additive manufacturing, that would potentially be very useful for us as well. But again, I haven't looked beyond, our case study has focused largely on this motor and this one part of the system. Honestly, I haven't looked at or thought that much beyond that in terms of how additional additive capabilities would help the overall tool. But I imagine. Hello?
Got it. Well, thank you. And with the limit here, I think maybe we we'll start wrapping up, just to be respectful of everybody's time. But first, I want to take an opportunity to thank Bill and thank Jim for their time and their knowledge and wisdom here this afternoon. I thought it was a great set of presentations, and really appreciate, as always, taking the time here to tell us about some of the work you do. Also want to thank NREL and the team at NREL for helping to administer today's webinar. Very much appreciated. For those who are interested, I saw a couple questions regarding administrative things for the prize. Again, anyone can enter the Geothermal Manufacturing Prize right now. The site competition is an open competition space. You can do so by February 17th. If you want to learn more about the prize, you can go to AmericanMadeChallenges.org and you can find the Geothermal Manufacturing Prize website there. Again, it's your clearinghouse for all your rules, how to enter, who can enter, who is eligible, as well as what you're competing for. So we welcome you to get in touch with us if you have questions, and look forward to continuing the conversation. Thanks, everybody.
Thank you.
Thanks.